Right, this lesson's all about making amines. So we know already if we look at ammonia, so here's ammonia. Ammonia's got a lone pair of electrons. So because it's got a lone pair of electrons, if you take another molecule with a slightly positively charged carbon atom on there, so imagine that's just part of another molecule there, then the lone pair of electrons can attack that positive carbon, which means that ammonia here can act as a nucleophile. Now, the way you need to think of amines is that an amine is essentially just ammonia, but one or more of these hydrogens is an R group. Therefore, like ammonia, amines can act as nucleophiles. So you need to remember that fact, because that fact's going to be really important in this particular lesson. Okay, what we're specifically looking at now is the reactions of ammonia with haloalkanes. And the reason why that's important is because this is how you make amines. So I'm going to put in brackets there, making amines. All right, so that's actually what we're doing. Okay, so let's have a look at a little mechanism now. So imagine I've got a haloalkane. So my haloalkane's here. I'm going to just put R group there. So that could be a CH3 or a CH2, a CH3, CH2. And I could pick any halogen, but I'm going to pick chlorine there. And I'm going to react that with ammonia. So this is a mechanism that you might have seen last year. Let's put some more information on here. We know there's a lone pair of electrons on this ammonia here. And we know that this carbon here is positively charged because that one there is negatively charged, because chlorine is more electronegative than carbon, so it pulls electrons towards the carbon, creating a permanent dipole here. So our first step is we have nucleophilic attack here, where this nitrogen forms a bond with that carbon there. We know that carbon can only bond 4 times, therefore at the same time this bond breaks. Let's draw what we make here. Okay, notice now I've got a positive charge on this nitrogen here. That's because the electrons go away from this nitrogen, making it positively charged. And I've broken that carbon-chlorine bond there, therefore the Cl- is on its own over here. Now, when you're seeing the reagents for this particular reaction, it won't just say reaction with ammonia, it will be the word excess ammonia. And because it's excess ammonia, in our next step, we can draw another molecule of ammonia. See, what I've done here is I've formed a bond here between that nitrogen there and that one of the hydrogens that's chemically bonded to this positively charged ammonia part of the molecule here, this nitrogen. And we have to break that bond there, neutralising that positive charge. Remember, nitrogen can only bond 3 times. So we've got 4 bonds here because of that positive charge. Okay, so this is our byproduct, this ammonium ion, this NH4+. And what that does is, that forms an ionic bond with the chloride ions here. So what you get is a byproduct of ammonium chloride. So this is when you react excess ammonia with a haloalkane. And you probably would have covered this last year. However, in reality, what happens is this primary amine which is produced, remember it's a primary amine because there's one R group, this is the R group, attached to that nitrogen here, so it's a primary amine. The reaction doesn't really stop there, not always anyway. So the primary amine produced is also a nucleophile, and this can react with a haloalkane. So it can react with another haloalkane. And particularly that happens when you don't use excess. So if you don't use excess, what happens is, if you don't use excess ammonia, you end up with more haloalkane left over at the start, because if all of the haloalkane doesn't react, what happens is the primary amine which is produced can act as a nucleophile. It can act as a nucleophile because of this lone pair of electrons here on this nitrogen there. And what that will do is this molecule here, this primary amine produced, will react with more haloalkane which we started off with if we didn't use excess ammonia. Okay? Obviously in a year 12 question last year it always said excess ammonia. Or if you don't use excess ammonia, what will happen is that will react with this. And I'm going to draw the mechanism now to show this. Okay, so here we've got our primary amine which is produced and some unreacted haloalkane. The primary amine can act as a nucleophile, just like the ammonia did in the very, very first step. So we get similar curly arrows, right? Watch this. So that nitrogen forms a bond with that carbon, and that carbon-chlorine bond will break. Okay, right, let's have a look at see what we've got here. Obviously we've got this chloride ion produced here. Let's see what else we've got here. So we've got an NH2 here, yeah. But remember, what we've got there is you've got what is essentially a secondary amine forming here. So essentially what's got secondary amine forming here. Watch how we make a secondary amine out of this. So we take our extra molecule of ammonia, okay, so this is now a secondary amine. It's a secondary amine because when you look at that nitrogen there, it's attached to one hydrogen and then it's got two R groups attached to it. So this is now a secondary amine. So you can form a secondary amine if you end up with some of this left over at the start. And that will happen if you don't have enough ammonia there to react with it all at the start. Now, the reaction doesn't actually stop there. So this secondary amine, again, can act as a nucleophile, because look, I've got a lone pair of electrons here. So let's do that over on this page here. Okay, so the secondary amine can act as a nucleophile, and it can react with even more haloalkane. Here's my second molecule of ammonia here, remember? All I'm doing here is just copying this mechanism, but I'm doing it to the secondary amine instead. Okay, right, now let's have a look to see what we've got here. So it's an amine again, isn't it? But this time there's no hydrogen atoms attached to this nitrogen here. So it's actually a tertiary amine. 1, 2, 3 R groups attached to it. And again, the tertiary amine can act as a nucleophile. Why? Because it's got a lone pair of electrons here. Just like the secondary amine did. Just like the primary amine did. Just like ammonia does. Okay? So if you can see a lone pair of electrons there, it will continue to react. So this tertiary amine here can then react with even more haloalkane. Watch what happens there. So it can act as a nucleophile because of that lone pair. Okay, let's have a look to see what that will do. Okay, so let's draw our haloalkane. Okay, now let's have a look to see what we've got here. So if you look at that nitrogen there, you'll see that there's no more hydrogens attached to it. So even if I did have any more ammonia, I couldn't just take off another hydrogen using this. Like I did here, took off that hydrogen. And like I did there, to take off that hydrogen. But I can't do that because there's no hydrogens left attached to that nitrogen there. So this ion here is stable. So long as you've got a minus ion to balance the charge, this ion here is stable. So what we've got here is we've got a structure which is essentially, it looks a bit like ammonia or an amine, but instead of hydrogens coming off this nitrogen here, or R groups, you've got four of them. Look, there's 1, 2, 3, 4 R groups. So what we've got here is we've got ammonia, a primary amine with 1 R group, a secondary amine with 2 R groups, a tertiary amine with 3 R groups. So we're going to name this, this type of molecule here, and it starts off with this word here. Quaternary, okay? Quaternary means quad, okay? As in 4. Now, this isn't an amine because it's got a charge, hasn't it? Amines are neutral molecules. This is an ion. So all of this, including the Cl minus here, this is called a quaternary ammonium salt, okay? A quaternary ammonium salt. Bit of a tongue twister that, but one way of comparing it is if you compare that to another salt based on the ammonium ion, and that is ammonium chloride. Now ammonium chloride is just NH4Cl. The quaternary ammonium salt has exactly the same structure as ammonium chloride, apart from instead of these 4 hydrogen atoms, you've got these 4 R groups on there as well. Okay, so we've made a quaternary ammonium salt, and at that particular point there, the reaction will stop. The reaction will stop. All right. So in effect, that reaction that you learn in year 12 here, where we use excess ammonia, if we didn't use excess ammonia, and instead we had extra haloalkane, then the haloalkane will react with the primary amine product, where the primary amine acts as a nucleophile here, to produce a secondary amine. Then that secondary amine produced can react with even more haloalkane to produce a tertiary amine, where the secondary amine acts as a nucleophile. Then this tertiary amine can act as a nucleophile, and it can produce a quaternary ammonium salt, where it reacts with even more haloalkane. And at that point there, the reaction will stop. Okay, so we can summarise this. And a nice summary is that a mixture is produced. A mixture of primary, secondary, tertiary amines and a quaternary ammonium salt is produced. So because a mixture is produced, it means that this is not a very efficient way of making an amine. Alright? So I know you learned it last year, but this is not the best way to make an amine. However, if we want to combat this, what we can do is we can actually separate the products using fractional distillation. And that's because the boiling point of the primary amine, the secondary amine, the tertiary amine are going to be different. The quaternary ammonium salt is actually going to be a solid. It's an ionic compound. So we can separate using fractional distillation, or in the first place, you can just use excess ammonia. Or we can use another method to make an amine. And that's what we're going to look at now, okay? A different method of making an amine, so we don't get all these mixtures of products, okay? So this is an alternative method to make a primary amine, alright? And the method that we use is a reduction reaction, and it's a reduction of nitriles. Okay, so this is actually a two-step process. Let's look at step one. Okay, so the first step you've come across before, and the first step is a nucleophilic substitution reaction, which you've come across before last year. Let's have a go then. So let's pick a bromo alkane. Here's a bromo alkane. And we use Cn- ions, which are cyanide ions. Remember the lone pairs on that carbon there. Good, so there we go. Here we've got our nitrile. That's our step one, and that's just a recap of last year. Then what we can do is, you don't need to know the mechanism of this, but this is your reduction bit. And it uses hydrogen with a nickel catalyst. So that's your conditions that you need to learn. So Ni is a chemical symbol for nickel. So we take our nitrile there and we react that with hydrogen. You need 2 molecules of H2 for this. And then what you get is you get the amine that is produced. And you can see that equation there is balanced. Okay, so you need 2 molecules of hydrogen there, because what we've done, if we look at this carbon here, has no hydrogens attached, and these are the 2 hydrogens here attached to that carbon there. And we need another molecule of hydrogen, because if you look at that nitrogen there, there's no hydrogens attached. You put 2 hydrogens there. So you don't need to know the mechanism for this. You do need to be able to write down an equation, and you do need to be able to write down the conditions. So it's hydrogen with a nickel catalyst for that particular reaction there. Okay. So just want to point out here that the resultant amine always has 1 extra carbon than the haloalkane that you started off with. So in this example here, what we've got there is we've got 1 carbon in the start material, but remember there's 2 carbons in the product, so just bear that in mind when you're answering exam questions. So that's just basically how you make it a primary amine. Excellent.